Good evening. Welcome to the Science for the Board. Tonight, David Paris will be speaking on geothermal energy. Dave is a retired aerospace engineer who spent most of his career developing and applying computational fluid dynamics methods for analysis and design of jet engine components and industrial compressors and pumps. He grew up in Queens, graduated from Brooklyn Technical High School, and earned engineering degrees in aeronautics and astronautics from New York University. He was a project engineer, managed software customer support, managed a group of design software developers, and retired as a director of software sales and marketing. Interesting. In retirement, he spends his time with family playing tennis, serving as chairman of the Long Island section of the American Institute of Aeronautics and Astronautics, and participating in PEIR, a retirees group that meets in libraries. Where he lectures on aerospace and other topics, has been a member of the Peer Council. He also lectures at libraries and schools. He's been a private pilot, Planning and Zoning Commission member, Boy Scout and Cub Scout leader, soccer coach and referee, Civil Air Patrol. I'm going to admit somebody in here. And amateur actor. Dave has been a NASA, JPL, Solar System ambassador since 2013. He's given many presentations about JPL missions. Take it away, Dave.
Okay. Thank you all for attending. This is a subject, I'm not sure what I came across, but I realized I knew next to nothing about it. So I thought I would look into it. And having done that, I thought I would share what I learned. So geothermal energy. Well, that's energy that comes from the earth. Geo is earth, thermal is heat. And the energy exists under the earth's surface everywhere around the globe. In many places, it's already used to generate electricity, heat homes and businesses, and it's also used in certain types of manufacturing and agriculture. It is a renewable energy, and that is in the sense that the amount of energy that's inside the earth is going to last for billions of years. Now, the sun is a renewable source, and the sun is going to last billions of years. So it's on the same order of magnitude as the sun. But today, very little of our energy use comes from geothermal energy. A very small part of it. And that hopefully will be changing. So I'm going to discuss the different types of geothermal energy, the advantages and disadvantages and problems of using it, and what prospects there are for increased use in the future. So this is a chart that I found that shows here's 2022. The top line is demand for energy around the world, and the colored portions are from different sources. So here's coal, oil, gas, natural gas, and you can see that around 2022, those are about at their maximum. And the reason they'll be going down in the future is because coal use will be going down. Don't see much decrease in oil or gas in this chart. So here's hydro power, that stays about the same, nuclear stays about the same. And what grows is solar and wind energy. You can see how much those are growing from the current. And this little dark thing at the top is everything else. And geothermal energy is included in that. Okay. But the other thing to also notice from this chart is how up until here, which was 2 years ago now, demand was being met by the energy production. And this anticipation is that that will not continue to be the case. So either we generate more energy or we have to decrease demand. And those are the only two ways we're going to get these two things to continue to agree. This is another chart and essentially shows the same kind of thing. This goes out to 2050. And you can see here that what's growing largely here is wind and solar. And also growing, but much smaller, is what they call geothermal biomass and other. So it's a second prediction that the fossil fuels use is going to decrease. This is actually showing a peak around 2030. But that should be decreasing. And the big thing that's going to be increasing is wind and solar. So let's see if that happens. This is a chart for the United States. And one thing to notice here is that here's the renewable energy, about 12%. And this is 2021 data, which was compiled last April. And here it shows that renewables about 12% of the use, and that geothermals only 2% of that, which means it's about 0.25% of the energy use in the United States. And the big things, of course, are petroleum, natural gas, and coal. Down here, and this is quadrillion BTUs. This is how much is used in electric power generation, transportation, industrial, residential, and commercial. So the main purpose of showing you this is just to put geothermal in the tiny fraction of energy use in this country that it has right now. This is a chart that gives you an idea of what the possible sources will be in the future. Solar, if used extensively, is estimated could provide not just all of the world's energy use, but 27 times that. There's enough energy hitting the earth from the sun to do that. And this is reasonably assured recoverable reserves, which they've said was, let's estimate out for 30 years, because that's a length of time commonly used when estimating coal and petroleum and gas use. So over the next 30 years or so, solar could satisfy all of our energy needs many times over. Wind could actually satisfy all of our needs, according to what will be reasonably technologically available. But the next thing after wind that they say is energy available is geothermal. So a lot more geothermal energy is available than is currently being used. And that's something to think about for the future. Now, I'd never come across this before, but after biomass is OTEC. I don't know if any of you know what that is. I certainly didn't. It stands for Ocean Thermal Energy Conversion. And this is not anything that's being used, I think, at all today, but it's to take advantage of the fact that in the oceans, the water being warmed by the sun at the surface is warmer than the water at depth. So there's a temperature gradient in the ocean, and any place there's a temperature gradient, there's a possibility of harnessing that for energy use. Okay. And this is renewable capacity additions. And this goes from 2017 up to this year. And what this is saying and this is in gigawatts, that photovoltaic is the big increase. This is the utility scale, and that is the yellow. And then distributed photovoltaic is also large. That's the orange one. So these two make up the greatest portion of what is anticipated to be capacity additions. And this, unfortunately, this chart didn't go out into the future beyond this year. But what it's saying is that, and this is essentially solar cells. It's saying that that's going to produce the largest increase in available energy over the near future. Okay. So let's talk about what geothermal energy is. From the Greek, geothermal would mean earth heat. So heat from the earth is what we're talking about. It's renewable. Its use is growing, but it's not growing nearly as quickly as solar and wind. Today, less than 1% of the world's energy consumption comes from geothermal sources. There are individual areas, and I'll tell you about some of those, where the percentage is much, much higher. But those are just small areas. So where is the geothermal energy? This is lava coming from the volcano in Italy. This is a water geyser in Yellowstone National Park. And this is just steam coming up from near a volcano. So it's available near volcanoes and at tectonic faults. Tectonic faults are places where the geothermal energy is easiest to access because it's closer to the surface. So the energy is in volcanoes at faults, but it's in geysers, hot springs, hot underground reservoirs. And those are the natural places from which we try and get geothermal energy. We also, in places where it's not that easy to get, we drill wells. And so we encourage the energy to the surface. And you can find the energy in some places in hot water, in other places steam. Some places there is no water or steam, so it's just hot rocks, but we can still make use of those for energy use, and also in magma. Now, steam technically is what you get when you boil water, when you vaporize water. But water molecules that are gas, you cannot see them. So how do we see steam? What we're seeing is the water droplets that form from all these steam molecules. So anytime you can see steam, you're seeing water droplets. Magma is underground rock that has been heated enough to melt. And then, so you get this melted rock and it has gas bubbles in it. Okay. And when that comes through the surface, that's what we call lava. Okay, so this is one of the pictures on the title slide. This is Bath, England. The Romans in around 60 in the Common Era built this. They built elaborate spas and baths, and it's heated by natural springs. So when the Romans discovered this in England, they put some effort into making a resort out of it. Okay. This is a picture of steaming food in baskets. And this is on the North Island of New Zealand. I don't know if these ladies dress like this every day, but for purposes of the picture, it looks very nice. So they're cooking. They're cooking meals in these baskets. And what's available there are these boiling springs, mud pools, there are geysers in the area. You can see the steam rising all around them here. So they're taking advantage of that. Rather than building a fire, they got all the heat they need and they use that for cooking. All of this, this hotness that comes through the surface is the result of tectonic activity beneath the Earth's crust. Okay. All right. So let's take a look at the layers of the Earth. The top layer we call crust. It's solid rock. And it's the rock is in tectonic plates. The plates over millions of years have moved around. If you look at the pictures of a couple 100 million years ago when the Americas were touching Africa and Europe, since then we've formed the Atlantic Ocean and we're now separated, but those plates are still moving around. They are 15 to 35 miles thick where there's land, but only 3 to 5 miles thick under oceans. Beneath the crust is the mantle, which is solid and magma. So it's solid rock and magma. That's 1,800 miles thick. And then beneath that's the outer core, which is hot magma. And that's 1,500 miles thick. And beneath that is the inner core, which is mostly solid iron and some nickel mixed in and some very smaller amounts of trace elements. This has a radius of about 758 miles. And depending on where you read, the temperature is either around 9,400 or 10,800 degrees Fahrenheit. Now, recent stories have said that the rotation of the core may have paused. And apparently over history, it does that from time to time and reverses rotation direction. So I'm not going to go into that in any detail, but just wanted to make note of it. The crust, with its tectonic plates that are moving all the time, as they move against each other, we get faults and ridges where two plates hit. And subduction is when the edge of one plate moving towards another one starts moving under the other plate. So the diagram shows that here and here. And with that happening, you get all kinds of currents in this magma. But these faults are the best spots for geothermal energy. And there's another paper that was just published that said they think there are maybe 100 miles down, there are streams of liquid magma moving around, and they may have something to do with the movement of the tectonic plates. I haven't read that whole thing, but that's something that just came out. Okay. So how do we get the heat in the Earth? Well, some of it's left over from planet formation, but the vast majority of it comes from radioactive decay. There are elements in there like strontium that are decaying all the time. And when they do that, they produce energy. Potassium is one that decays in, yeah. Okay, so that's always going on in the core, and you get the temperature in the range of 10,000 degrees Fahrenheit. That heat, it radiates outward because it's hotter further in, so it's radiating outward. And as it does that, it warms the rocks, the water, and the gas that's in the mantle. At the surface, the geothermal gradient is about 1 degree Fahrenheit per 77 feet, or about 70 degrees Fahrenheit per mile. That's not constant as you go down. If it did, you'd get to much higher temperatures in the core. But anyway, near the surface, that's what the gradient is. However, it can be a lot higher if you're in a geothermal reservoir. So if you're in an area that's been heated up by the internal core, the gradient could be much higher. So, advantages of geothermal energy. For one thing, it's renewable. So it's not going to run out, as our fossil fuels will. It's reliable. The heat source is constant. You go down a little bit into the earth, and the temperature's pretty constant year-round. It's always available. It's not like wind and solar that only provide energy for you some of the time. It's always there. Not subject to weather. And it's spread out all over the world. There are sources pretty much everywhere. Some much easier to get at than others, but it's everywhere. And it produces either very little or no pollution at all, which is a huge advantage. When you build power plants to use geothermal energy, they can last for decades and centuries. Yeah. The power plants, when built, they are smaller than power plants using other forms of energy. And not only that, but they can be scaled up and down, and they can be made much smaller than fossil fuel power plants. Okay. Now, the energy doesn't get used up, but in reservoirs or pockets, it can diminish if the energy taken out is faster than the energy that's being supplied to that reservoir. So there are places, and I'll mention a few, where the amount of energy is decreasing in time. The cost of building geothermal plants is high, but the cost of operating them is very low. You're not buying any fuel. Okay. So what is the disadvantages? Well, you can get small earthquakes. When you build the power plants and you drill into the ground and you push cold water down through these wells. It can crack the rock. It can increase the size of cracks that are already there. And they have had small earthquakes, nothing major, but there's one example of a project in Switzerland where the earthquake started to become too much of a problem and they closed it down. They closed down the geothermal power plant. Subsidence happens also. You're making all these changes to the crust, and sometimes the land can start sinking slowly, but it can start sinking, and that can have effects on other uses of the land. You can get small amounts of hydrogen sulfide and carbon dioxide released. If you don't properly insulate the reservoir, the water that's in it can go over and absorb toxins. And so they can come up to the surface and can be released. So that is one caution. I said the installation costs are high, and the risk of creating a new power plant are also high. And so investors get discouraged by that. So what are some of the problems? Well, to produce energy, you need on the surface, you need the heat near the surface. And that's only true in maybe 10% of the surface. It's all over the place, but it's not every place. It's particularly available along fault lines. But in many places, when you look for that energy, it's too deep. If it's 1 or 2 miles underground, that's generally thought of as accessible. But working far under the ground is difficult. You need to explore to find sources. And once you find them, you're working with very high temperatures and pressures, and that is technically difficult. The equipment has to be able to work in those conditions. The high expense of exploring and drilling definitely discourages investment. And so the risk of success it discourages them as well. So what are these risks? If you want to drill holes deep into the surface, going down miles, that gets expensive. You might find a place where you think you're going to find a suitable heat source, and maybe it doesn't turn out that way. When you find a source, it might run out. And that's especially when you try to extract more energy than the Earth is putting into that particular source. It's expensive to put the heat pump pipes into the ground. And I'll show you some more detail of that. If you have a test well, you may not be able to use it. As I said, the equipment has to withstand the high temperatures and pressures. And if you don't want to get the locals upset, you don't want to build it where they think there's a beautiful scene. So that's another constraint. So how is geothermal energy used? Well, there are 3 main methods. The direct, the heat pump method, which is the second most commonly used, and the energy source to produce electricity. And that is the most common use of geothermal energy. The big advantage of the first 2 of these, they produce no pollutants because there's no fuel burned. You do have to use some electricity to run things like pumps, but no fuel is being burned right there. when you produce electricity from geothermal energy, you get very little pollution. But in all cases, the power plant has to be built near some hot underground reservoir. Okay. So, producing electricity, and this is the most common method. Currently, I think this was from last year, 26 countries are doing that. If you're going to produce electricity, that's good because the users don't have to be local. Around the world, something like 11 million homes are using geothermal energy for their electricity. That number might be higher because I didn't get this year's numbers for everything. This uses water that's usually 300 to 700 Fahrenheit degrees. And you put your power plant near the heated water or steam that's underground. You drill the well or the wells into the reservoir 1 or 2 miles deep. Down there, the pressure is very, very high, and it keeps the water liquid. So you bring that up through your pipes, and the hot water or steam at the surface can be turned on turbine blades, which spins the turbine, and the turbine then spins a generator, which gives you the electricity. Sometimes they use 2 well systems. You send the cold water down through one, and you bring the hot water up through the other. The first geothermal electrical plant was built in Larderello, Italy, opened in 1911. It's a dry steam power plant, and dry steam is the steam that doesn't have any droplets in it. So you bring up dry steam and you send it to this turbine and you generate electricity. Since the 1950s, the steam pressure at this locality has dropped by about 25%. So you can see this looks like a large power plant. And so they're taking energy out faster than the earth is putting it into that underground reservoir. But about 1 million people are getting their electricity from this power plant. So as I said, there are places where the use is significant. It's just not that many places. And they do get minor seismic events in that area. So as long as they're minor, minor is usually like 2 to 3 on the Richter scale. So that's the kind of thing that doesn't really shake anything or break buildings. Okay, direct use. That's possible anywhere you find an underground reservoir. You bring the heat up straight from the ground. It comes up in hot springs and pools or geysers. And people have been using that for bathing, for cooking, for heating their pools, their houses, and all these other things, including sidewalks and roads in the winter. It keeps greenhouses warm. They use it at fish farms, drying lumber, and processing fruits and vegetables. So it has a wide range of uses. Or you can drill 2 deep wells. Now, this direct, in general, you drill 1 well and you bring the steam or the hot water up and use it. But you can drill 2 deep wells, so you pump water into one. The water goes over hot rocks, it heats, gets heated up, and then you bring it up to the surface and you recycle it. And of course, there are also tourist attractions that use the direct geothermal heat. The second use is heat pumps. About 70 countries now using heat pumps. Heat pumps can be used to heat or cool buildings. It's very energy efficient. And this was started to be used in the 1940s. So there are pipes under the ground, maybe 6 to 8 feet below the ground, and the temperature is pretty steady there, 55 to 60 degrees Fahrenheit, year round. When the surface freezes, that's just the first 2 or 3 feet, so it's above this. And a single system can be used to heat or cool houses. When we're finished, I just found an hour ago some better pictures than the ones I have in here. If I have time at the end, I'll show them to you. Now, the heat pumps can use either horizontal pipes at the ground, which only takes a couple of days to install, but requires a greater land area than when you put them in vertically. But that takes longer. You have to dig deeper. But it doesn't require as big a heat reservoir underground. So a heat pump is a device that takes thermal energy from one place to another. In a refrigeration cycle, refrigeration cycle is the cycle that the heat pump uses, and that can run either forward or backward. So you can heat a building or you can cool it. If you're only cooling it, we call that an air conditioner. But a heat pump can do either, and all you have to do is reverse a valve. So it has a closed loop. Most of them have closed loops with one end inside and the other end outside the building. You circulate a fluid through that loop. You cool that liquid in one place and release the heat in another. I said that backwards. I'll show you the picture. It's clearer with the picture. In the heating mode, you compress and heat the fluid outside. Then you evaporate and cool it inside. So you're transferring the heat from outside to inside, even though if you're doing it with a air heat pump, you're taking heat from air outside that you may not think is hot. But by using this fluid, you're able to do that. And then you complete the cycle. Very energy efficient technique, much more efficient than using fossil fuels. All right, because you're not burning anything. All right, so here's a picture, and as I said, I found a better picture, but I didn't get a chance to put it in here. So what you're doing, this is as an air conditioner, using a heat pump as an air conditioner. So outdoors, you send this fluid through a coil, and you're expelling heat into the air. So what's in the coil is hotter than the outside air. And then you send it through this expansion valve. It liquefies and cools. And then inside, you send air over these coils. The air goes over the cold coils, gives up its heat to the coils. And so the cold air is what air conditions your house. Then you send this gas back to a compressor. It goes around, and it's a closed cycle. This is the vapor compression cycle that applies in heat pumps, refrigerators, and air conditioners. And it's interesting because Engineers and physicists like to use this type of a diagram to describe the process. But one of the problems with this is, and I guess it's von Neumann who said, nobody really understands entropy. No one knows what entropy really is. That's what he said. But in any event, here's entropy, and here's 5 steps in this process. And these correspond to the picture I showed you of the heat pump. So starting at 1, you compress a vapor, the temperature goes up. And here you can see the pressure. These are isobars, so you're also increasing the pressure. From 2 to 3, the vapor removes some of the heat, so you can see there's some cooling here. Then in this condenser, it's condensed into liquid. So in this part of the process, there's a mixture of liquid and vapor. And then it becomes a saturated liquid, and then you go from here to here, across the expansion valve, and the liquid flashes into liquid and vapor. So some of the liquid becomes vaporized. And then the last step is you go to all vapor. So this is all vapor, this is all liquid, and there's the mixture in here. Anyway, that's the temperature entropy diagram for the process. So let's talk about the geothermal heat pump. This can be used just about anywhere in the world. You drill 10 to 300 feet into the ground. You don't have to fracture bedrock for this system. In general, there's a closed loop, one end in the ground, the other end in the building, or whatever you're trying to transfer the heat to. The fluid is circulated through the loop, transfers the heat, very energy efficient. And this is possible because the ground temperature is about 50 degrees or 50 to 60 degrees, which is warmer than the air in the winter and colder than the air in the summer. And that's just what you want to operate your heat pump. The Environmental Protection Agency called geothermal heating the most energy efficient and environmentally safe heating and cooling system that we have available. So there are 4 types of heat pumps. The first 3 are closed loop, and the last one's an open loop. The closed loop puts these coils in the ground either horizontally or vertically, or in a pond or a lake. The open system just takes the water directly to and from the ground. So there's a, I don't know if you can see these arrows. This is one where you pump into the ground. It gets heated up in the ground and goes over to here, and then comes back to the house. So there are 4 types of systems. Just want to briefly mention, low temperature geothermal energy comes from heat about 300 degrees Fahrenheit. It's available in lots of places a few feet below the ground, and it's used for heating greenhouses, homes, fisheries, and industrial processes. Okay, so let's talk about the different types of steam plants. In the flash steam plant, high pressure hot water is pumped to the surface and flashed into steam to run the turbines. The cooled water is then returned into the ground, and most geothermal power plants today are of this type. Then there's the dry steam plant, and that's a very simplified picture of it. The underground steam comes to the surface and drives the turbine, which drives the generator, which produces the electricity. And that's the first plant in Italy over 100 years ago. Then there's the binary cycle. Hot water is brought up and transfers heat from one coil to another to a fluid with a lower boiling point than water. And that's what is used to drive the turbine. And this can use water between 225 and 360 degrees, which is cooler than the water that's used in the flash stream or dry steam plants. And these reservoirs are more common than the 600 to 700 degree reservoirs. So it can be used in more places. Then I found this diagram. This is for a dry steam, and the reason I like this is it includes in it the mention of pumps and the cooling tower and the fan. So the pumps and the fan all require energy to run, but much less than the amount of energy than what comes out of the system. So you bring the, from the well, you bring the hot water up, you get any sand out of it, you get the water drops out of it, you send it to the turbine, then you condense it, and you send it around again, back through the well that takes the water down into the ground. Okay. One example of a dry steam power plant is the geysers in California. Now, there are no geysers at the geysers. Why they named it that, I don't know. Maybe just saw some steam coming up. The steam is piped directly to a power plant, runs the steam turbines to produce the electricity. Okay. And that's the dry steam. But the most common type of geothermal power plant is the flash steam plant. And so here you bring the hot water and steam up, you flash it, so you get all steam, that runs the turbine, the generator, and produces the electricity. Water is pumped into the ground. All right. That's what this flash tank is for. Evaporates the water into steam, runs the turbine. Okay. And there are plants like this in Iceland, the Philippines, and other places. Here's a picture of the binary cycle where you pump the water down, you bring the water up. There are coils here. This is the heat exchanger. The heat is transferred to this fluid with the lower boiling point than water, and that's what runs the steam turbine. So this can run at a much lower temperature than if you were doing this directly. Okay. Yeah, and they use organic compounds in this second cycle. Yeah. But the only emission you get out of this process is steam. You don't get pollutants that cause global warming. And the water goes back into the ground, so It's a cycle. This is a binary cycle power plant in Empire, Nevada. It's interesting to me that this looks, compared to fossil fuel power plants, tiny. If this is the whole thing, then boy, it's really small. Co-produced geothermal energy. This is where you have other energy sources. So if you have an oil or gas well, that uses water, and the water is heated, and in the past it was pretty much thrown out. Not any use made of it. But in the US, we get about 25 billion barrels of hot water every year as a byproduct of these oil and gas wells. The steam from that can be used to generate electricity, and they're currently working on systems to make this portable. So it would have, as a portable unit, it would have tremendous potential in poor and isolated communities. So here's a list of uses for geothermal energy. Where were we? In Costa Rica, I swam in a swimming pool that was heated by hot springs. District heating systems. So this is where you bring the hot water up and you distribute it to a community. And that's what they use in Reykjavik, Iceland. Greenhouses can use geothermal water to maintain constant temperature. There are a number of industrial processes that use low heat and constant heat. Timber drying, fabric dyeing, and taking gold and silver out of rock all use low heat processes. Also drying fruits and vegetables. Heating agricultural fields with underground pipes. So you don't have to send the pipes into a house. You can do that. And fish farms. So you can heat the water in the fish farms. And I assume tropical fish really like that. In the USA, we are the world's leader in electricity production from geothermal energy. It replaces about 25 million barrels of oil annually. The government has made it a priority. It's available, however, mostly in the western states. And these are the 7 states that currently have geothermal power plants: California, Nevada, Hawaii, Utah, Oregon, Idaho, and New Mexico. Perhaps in the future, there'll be more. California is the biggest user, Nevada is second. And in the US, it produces enough energy for about 3.5 million homes. In Yellowstone, there are geysers, but Yellowstone's a national park, so we can't build a power plant there. Or at least so far we can't. But in Northern California, those are the only 2 underground steam sources in the United States. It's called geysers in California, but there are no geysers there. It's a dry steam power plant. And at one point was the largest geothermal power plant in the world. I'm not sure if that's still true. They have 350 wells and 22 power plants. And that's why it produces so much energy. Then in the Sierra Nevada mountains, they produce power for about 40,000 homes. In Hawaii, about 30% of the Big Island's energy is produced from geothermal. Pinewood Forest in Atlanta, 1,300 homes using a ground source heat pump system. And that's the first large-scale community in the United States. Up to 10% of our energy needs could come from geothermal sources in the future. I'm going to go briefly around the world. Costa Rica, 13% of their energy is geothermal. Mexico is the fourth biggest producer in the world. And they aim by 2024, next year, 35% of their energy needs from geothermal. That's because they have 25 volcanoes. So there's a lot of hot magma there. Chile is the largest undeveloped area in the world in the mountains. And they opened their first geothermal plant. Argentina, they use it for greenhouse heating. In Europe, it's very patchy. There are not many good areas, but there are already 130, as of 4 years ago, 130 geothermal power plants. There's 6 innovative projects last year. In general, they use it for greenhouses and fish farms, and there is a European Geothermal Energy Council that's looking at future uses. Iceland is the most outstanding country to use geothermal energy. And the volcanic activity there produces all this molten rock and magma. In a small area, they have 6 flash steam power plants and provides over 90% of the heating and electrical needs for the whole country. Of course, there are only like 335,000 people in Iceland, so it's not a major thing in those terms, but they are sharing what they've learned with the rest of the world, so that's a good thing. Germany, they use underground heated water for electricity generation. And here's a picture of one of those plants in Iceland. Turkey is the bigger producer of geothermal electricity in Europe. They use it for electricity generation and in their greenhouses. Hungary, 80% of the energy that vegetable users use comes from geothermal. In the Netherlands, they're heating bike paths in the winter. In Italy, farmers use it for their farming purposes, and they've been doing that for 100 years. Yeah. France is interesting because in the Paris area, geothermal district is heating 1 million homes. And there are over almost 2 million ground source heat pumps. And that's as of 6 years ago. I'm not sure what the number is, but from another source, 400,000 heat pumps were installed in 2020, although not all of those are geothermal. Poland, good place to increase geothermal heating. Philippines, that's on the Ring of Fire. They have 14% of the country's electricity from flash steam geothermal power plants. And they've been doing that since 1979 and still operating. Now, the Philippines, of course, has a much bigger population than Iceland. Indonesia, large potential. They've identified a lot of power plant locations, but they're not all built yet. They'd like to be first in the world. In Japan, where just about all the land is being used by the population, large projects have been resisted, but there are small plants in operation. So that's good. And Japan's a good place for the geothermal because you can build small power plants. China has the largest number of geothermal district heating systems, and they dig deep geothermal wells. New Zealand gets about 17% of its electricity from geothermal sources, and they use natural geysers and steam vents. And they use it for all these things and for prawn farms. There's a picture of a prawn. Okay. They dry timber with it and they process feedstock. And it's interesting, this is the only example of African use, but there's a 4,000-mile fault line that goes through Kenya, and there's a string of volcanoes. So they built a power plant with hundreds of wells where they dug a mile deep, and they get half the country's electricity from that. All right, I'm going to finish up with some things looking to the future. Ground source heat pumps. The efficiency is improving. When you dig looking for a heat source, you have to have heat sensors in the drill bits. And when they detect the rise in temperature, you stop drilling and you see if that's a usable source. Okay. They're coming up with better designs for the coiled pipes that go into the ground, so that it uses less land space. Working on new methods for extracting valuable minerals. Better drilling methods, new drill tips, motors, and better processes for dealing with those very high temperatures and pressures. Pressures can be on the order of millions of atmospheric pressure. And there's laser assisted drilling. I didn't get any details on that. Then there's the earth gun. You fire rounds into the ground. When you set up the process, you use liquid carbon dioxide, which works very well under pressure. And it's better heat carrier than water. And it doesn't dissolve minerals. Water dissolves almost everything. So the prospect there is maybe you can put these geothermal plants in more places. Enhanced geothermal systems. You put an injection well down into the dry rock. You pump cold water down there into cracks that are already existing, or maybe you create new cracks. You heat the water to about 600 degrees Fahrenheit, 2 to 3 miles below the surface. You bring that water up, and you either put the steam or the secondary fluid to turn turbines. And then you recycle the water into the ground. This may open up new areas for power plants or expand the use of existing power plants. But it can cause small earthquakes because you're pumping cold water into cracks in the ground. The Department of Energy has got a $220 million investment at the University of Utah. And there's a European project to develop deep geothermal energy for new heating networks. And that's a picture of Desert Peak, Nevada, testing an injection well. I'm not sure what the guy is doing. It looks like he has a board here, but I don't know what he's doing. So current positive signs. And I got, all right. 5 years ago, Coca-Cola said in the Philippines, they'd use geothermal electricity. The World Bank report from that same year said reserves in Latin America and Caribbean, they're unused reserves, and we should start looking at it. The UN report was positive about the prospects for Africa. Iceland is sharing what they've learned with the rest of the world. Germany and Turkey are working together to develop technology and looking at business opportunities. As of 2019, Turkey had the fastest growing geothermal industry in the world. Although in Europe, France is producing the most most geothermal units for homes. And in Mexico, there's a Center for Innovation in Geothermal Energy, where they brought together 150 experts, and they've got 30 projects going for Latin America. So these are some other positive signs. Our Department of Energy has a deal with New Zealand. New Zealand is planning to be 100% renewable by 2050. There's this international partnership involving the United States and these other countries. Iceland is looking at new systems to drill deeper near volcanoes. And that would be working with dry steam. And they point out that dry steam is 10 times more, has 10 times more energy than wet steam. So if you use dry steam, you don't have to disturb as large a ground area. More and more homes are being built with geothermal sources for heating and cooling. And the cost of geothermal energy technology has gone down. So it's becoming more possible for both individuals and companies. So for the future, we need a system of international rules. I tried checking and I did not find anything. Mexico has some laws, but there's no international set of rules. Especially in poorer countries, government funding is absolutely necessary. Two very good areas along which to look at this, along the Pacific Ring of Fire and the East Africa Rift Valley. Heat pumps could satisfy 80% of the global space and water heating needs, and would have a lower carbon footprint than fossil fuels. But as of 2021, only 10% of the world's space and water heating needs are being served by geothermal. Mexico plans by next year to have 35% of their energy needs geothermal. And there's tremendous potential of the co-produced geothermal plants. I think there are oil wells in lots of impoverished countries. If they could use the heated water that's a byproduct, that would be great. And the National Science Foundation and Department of Energy have a partnership for geothermal internship in interns, where they're going to, in 6 months, teach these interns what they need to go out and be productive innovators in geothermal energy. So in summary, geothermal energy has great potential: renewable, reliable, flexible source of electricity, heating, and cooling. There are resources around the world. The barriers that have existed before, we're working on getting rid of them. You already have enough electricity to power more than 2.7 million American homes, and 80% of the global space and water heating needs could be satisfied with geothermal sources, but today it's only 10%. So we're counting on advanced technology and government incentives to increase the use of geothermal energy in the world. So that's it. I only ran a few minutes over because we didn't start exactly at 9:30. So let me stop sharing. And I'd like to hear your comments. And if you have questions, I will attempt to answer them. Anybody?
It's been a while since I've seen that temperature entropy curve. We had to run a lot of, Tim Wenzel and I were in mechanical engineering together with Professor Tuttle at the University of Vermont. And we had to run those run those equations
And,
Yep. and look everything up in the tables and all that.
okay, so my question is, when you use those diagrams, did you understand them?
Oh, well, like you say, I didn't know what entropy was, but I knew how to, I knew how to get the answers. Yeah, I was actually pretty darn good at it
Okay,
at the
okay,
time. Yeah,
well,
and
I'm not-
it's pretty understandable if you stare at it enough.
I'm not sure what year von Neumann said that, but it's a lot of years ago. So it may have changed. I'm looking for the numbers. Yeah. If you have a couple minutes, I would like to show you this. I didn't get it.
You
Share
flashed it at us.
Share screen. No, that's not what I want. I want this. Okay. Can you see that?
Yeah.
Okay. All right. This is what I wanted to show you. This is heat pump that can be used for both heating and cooling a house. So you have coils out inside, you have coils outside. And what you do to change from heating to cooling is you turn this valve 90 degrees. And what that does is it reverses the flow of the coolant through the system. And so instead of being heated outside, it gets cooled outside and vice versa. So that's what I liked about this diagram. It doesn't have all the detail of one of the other ones I showed you, but it's
That's
the only
basically
one.
it.
It's the only one I found with this picture of this valve that you rotate 90 degrees. And whoever came up with that gets my applause.
Understandable.
Oh, so where's the expansion valve? The expansion valve always goes on the evaporator.
Yeah, right there.
They show it here. So in one case, you've got the fluid going in from this side, and the other side, the other way, you have it going this way. Yeah, and I think, I don't know. You have to turn this valve.
Right.
I don't know if there's anything that has to be turned here.
It doesn't look like it, except it's a double way expansion valve.
Oh, okay, right.
Yeah, and we could have a whole lecture on how a heat pump works in your house.
Yeah,
Tim Wenzel could do that.
They have a coefficient of performance of over 3, which means that they put out 3 times as much heat as they consume in electrical power.
Yeah,
okay.
It's pretty amazing.
It is.
We were quite surprised when Dave gave this talk to a group that's out of Hofstra University, that a number of people said, oh, I have a heat pump. Now, this is Long Island. We don't have volcanoes, but this was heat pumps, and they're putting them under their homes. And they were talking about how easy it was to switch between heat and air conditioning, because we need both here, we're living in New York. And that was fascinating to know that these people have it right here, that we know. But we live in a co-op community of 3 huge buildings, and I'm sure it could be done here, but I would guess that the board would not entertain this idea at all. And it's a shame, because our systems here are antiques right now. Dave and I freeze in the winter, and it just, what are you gonna do? But anyway, I'm fascinated as we were in Costa Rica, and that's what I got my first taste of living in a country that really embraces using their geothermal energy. They have lots of these hot springs that are natural, like Dave was talking about. You just jump into them and go swimming. So it's kind of cool.
Yeah.
Okay, and
I have a question, it's related, but it's slightly off topic, I guess. With a heat pump hot water heater, if we think about it in the summer, it's putting out cold, so it's helping to cool your house. But in the winter, it's also cooling your house. So if you have a heat pump system that's heating your house and your hot water system that's cooling your house, is it still more efficient because of the coefficient of, say, 3, if it has that system? But if it had a coefficient of, for instance, 1, wouldn't that be a net neutral?
yeah,
Well,
one would be, but you're saying you use a heat pump to heat your hot water
yes,
and another heat pump to cool the house in the summer?
Right,
that's
because
two
in
different
the
heat
winter,
pumps.
that hot water heater is cooling your house.
it should be in the garage.
Yeah.
Yeah.
I don't think you use hot water to cool your house.
No, he's
Um,
saying that the heat pump itself is a self-contained heat pump hot water heater puts out cold air as it heats the water.
Yeah, but that's not enough to cool your
Shouldn't
house.
be. It shouldn't be.
Yeah. So,
It's code requirement nowadays.
yeah. All right, guys. Thank you for your attention.
Yeah. Thank
And,
you. It was very understandable, and I think it was fun to go through all that. That's good stuff.
what are our prospects for the future?
Well, Cindy and I are going to Hawaii
Ah,
next month, and we don't have any other talks for a while, so we'll see. We'll see what people come up with. We're
okay.
gonna take a little break, I have a feeling.
All right.
And but definitely this has been a lot of fun this season. So what the heck? Thank you so much, Dave, for coming forth and doing this.
Let me tell you, Bruce, we have enjoyed all of the lectures we've attended. I think it's a great thing you're doing, and after Hawaii,
Yeah.
let's do what you can to get us going again.
Okay.
I agree.
Thank
Okay.
you.
You're
Bye,
welcome.
everybody.
Bye-bye.
Bye.
Bye now.